Okay, let us start experiment number 6, image formation of mirrors. So you can download the lab manual from the week number 9 folder, and also the data sheet. So let's start with the plane mirror first, okay? All right, so what mirrors does is it reflects all the light rays back into the same medium where the light rays is coming in. So let's take a look at the plane mirror. So the very basic ideas are the plane mirrors. We need to check the ray diagrams to identify where the image is. And the image should be virtual because image going to be on behind the mirror. And whenever the image forms by the extended rays like this dotted rays, that kind of image called the virtual image. Anything you measured from the mirror to the extended ray direction, those numbers going to be come with the negative sign because of the sign convention we created for the mirrors and lenses formulas, okay? And anything we measured from mirrors to the real ray directions, those comes with the positive sign. Okay, so let's take a look the plane mirror. So to do that, we need the simulation on page number 3, very top. Let's take a look at the simulation. Okay, so the simulation should be look like this. And you should click on show image right here, show control points, and also the show grid. So then you can see when you switch on the grid, it look like a graph shape, but these numbers has no any meaning, okay? So it just tell you equally distributed the numbers. We can put any unit accordingly. And also the negative and then positive sign has no any meaning right now. So the sign with the measurements, we have to give the sign according to our sign convention, okay? And let's click the show, before you click the show incident rays, you should click this object right here. See, when you bring the cursor on top of the object, you can click and drag object anywhere you like, right? So just click and drag bottom point of the object onto this horizontal line. Now we'll consider that is our principal axis. And then change the top of the object to about 2 squares in height. Now you can see object and the image going to be exactly the same in height, right? So the size is going to be the same, which means the magnification from the plane mirror going to be always 1. And let's switch on now the show incident rays. Now you can see there are 3 incident rays, right? Actually 4 incident rays, 2 come from the bottom point and the 2 come from the top point. You can change the rays where it actually intersect with the mirror if you wanted to, but we can't really add or get rid of any rays because this is a presetting in this simulation, okay? So they are going to be always 4 rays. And we can change actually where the rays are actually hit on the mirror, okay? And we can do it like this maybe. One ray, 2 rays, is one is starting from the top, one is starting from the bottom, exactly parallel to the principal axis, and the 2 other rays are angular, but when you take in the angular, do like about 1 square because we try to get the incident angle and the reflected angle by using this one. So if I have measurable values, that's going to be easy, okay? Then now you can see the rays must be reflected right after hitting this. So you have to show normals. Then you can see the orange lines are the normal lines. And if you click the show reflected rays, you can see that green lines, those are reflected rays, right? Whenever the optic ray hits perpendicular to the mirror, it reflected back itself, right? These 2 are going back itself. Now these 2 are reflected with the same angle. See that? Yeah. Now, to identify the image, what we need is actually virtual rays. You can see image not going to be anywhere on this side. image should form on the other side. To identify that, you should click on show virtual rays. As soon as you click the virtual rays, you can see all of these 4 rays are extended with these red dotted lines. So those are not real rays, right? We extending where it's supposed to be originating. It's look like it originating here. So that's the idea of the virtual image. So the image produced because of the extended or extrapolated rays called the virtual image. And that's it. It's very simple. And then I think we should take a screenshot of this one too. And then we need to complete the table number 1. To complete the table number 1, all we have to do, change the object location and then measure the image distance, and then the object height we know 2 is squares, and then we have to check as we change the object location whether it's changing the image height or not. Okay, that's all. So let's do that. Right, so now let's start. We need about like 5, 6, 7 data point, 6 data point. Let's bring a little bit closer to this one towards maybe number 2 location. Let's assume that number 2 is about 2 centimeters. Okay, you can see, you can click this and then drag anywhere you wanted. As close as you comes, your image comes closer, and then as far as you move this image, go further, but the size of the image doesn't change at all, right? So that's the idea. It's a very simple concept. Okay, now let's write it down. Okay, let's write it down. Image distance measured in meters, and then object distance measured in meters, image also measured in meters, height let's measured in meters, and HI measured in meters, image height, and the incident angle and reflected angle we can't measure directly, but we can calculate by using these numbers by taking the tan of this angle. Okay, so those will measure in degrees. Degree sign you can find. Usually that's going to be, if you go into insert and then go very corner of right hand side, the symbols, you can find the degree sign. So let's insert that on there. Okay, so that's the unit degrees. All right, so let's start from 2. I'm gonna assume each of this number represent 1 centimeter. Okay, this square is 1 centimeter square, so which means this is 2 centimeters. And the image distance is going to be also 2 centimeters, but image distance, you can see you are measuring to the left hand side, which is not the real optical rays. Because of that, that should be negative 2 centimeters. Okay, that negative sign is because of the sign convention we created. And also let's add 1 or 2 decimal places more. You can't measure directly more than 1, but since I have 1 and 2 these lines, I can definitely measure at least one number in between. We can estimate in between. So because of that, let's add 1 decimal place at least. Okay, that will be our accuracy. In this case, 1 decimal place. All right, and then let's continue. Object height also 2 is squares. 2 is square means 2 centimeters, and the image going to be the 2 centimeters. And angle we can measure by using, actually you can see, for example, let's say I want to measure the angle here. Incident angle gonna be this angle right here. So this is the normal line. So the angle, this one from blue line to the orange line, that's the incident angle, right? I can measure that by taking the tan inverse of y and x, right? If this angle is theta, this angle is theta, which means theta is equal, theta incident is equal, inverse tan, arc tan, a tan parentheses, and this number we need in degrees, right? So the always Excel will give us radian value, so I have to use the degrees command first. Degrees, then arctan, then parentheses y over x. Y is 1 square, that is 1 centimeters, divide by x is now 2 squares, that is 2 centimeters. Close brackets twice, hit enter. So that's about 26.6 degrees. And theta reflection also I can calculate the same, maybe the angle between this green line, this arrow, and the orange line right here. So that's going to be about the same then, right? Let's do it with degree function first. Degrees, parentheses, arctan, parentheses, that also the same, 1 divided by 2, close brackets twice. So there's no difference at all. So what it confirms is the reflection law right here. Okay, then all we have to do, click and drag object into a next location. Let's say next location is 3 squares, 3 centimeters. Image also at 3, but it is 3 negative because that negative sign come because it's a virtual ray. Okay, anything measured from the mirrors to the virtual ray is going to be negative, and the height is actually same, nothing changes. We can do arctan equal sign degrees a tan parentheses. Now incident ray right here, first ray I'm talking about, this blue ray right here. So the y is still 1, but the x is now 3. Okay, so the 1 by 3, close bracket twice. Incident angle is about 18.4. Reflected angle equals sign degrees parentheses a tan parentheses. Reflected angle going to be right here, the angle between the orange and first red line. So that's going to be again 1 over 3 y over x. So it must be the same because it's a plane mirror. Okay, then all we have to do, click the object and then drag to the next location. 4 centimeters, -4 for the image distance, and the height doesn't change at all. And this is going to be then equal sign degrees a tan parentheses, now 1 over 4. And then you continue equal sign degrees a tan parentheses 1 over 4. And the next object location, click and drag to your left hand side, each one is square at a time. Okay, 5 and then -5, and then height doesn't change at all. It's going to be equal degrees a tan parentheses, and now 1 over 5, and the reflected going to be the same, but we'll do the function anyway. Degrees a tan 1 over 5. Let's do 2 more locations. You can click and drag further if you want to, but I'm gonna go into the next number, that is 6 minus 6, 2 and 2. Height doesn't change at all, and angle of incident now equal degrees a tan parentheses 1 over 6, and equal sign degrees a tan 1 over 6. And we'll do one more data point. This is just to observe how the image formation behave. Next, we're going to actually draw the image, the ray diagram ourselves by using another simulator. Okay, and now it's going to be 7, -7, 2 and 2 doesn't change at all, equal degrees tan parentheses now 1 over 7. 7, and then the reflected angle also the same, degrees a tan 1 over 7. Okay, so that confirmed, the law of reflection is confirmed. And also the image height and object height is same, doesn't matter where the image object is. That confirm the magnification, and also the magnification we can do di over d0. That will confirm di is, because if I use in the di, then it's going to be magnification negative di over d0. Negative negative cancels out. You can see magnification again, the positive one. That positive one magnification means this is an upright image. Okay, that's the idea. Okay, let's go into table 2. In table 2, what we're going to be doing, we actually going to do the ray diagram of the same plane mirror, but by using a different simulator. We're going to create the ray diagram what you observed earlier ourselves. Okay, click on this simulator right here. All right, now you can see a new simulator, and in that simulator you have to reset first. Okay, reset the whole thing, then let's draw that diagram. All right, now how to draw anything here. What we like to draw is the plane mirror and the object and the incident ray. Okay, and then by using the extrapolated rays, we try to identify the image position, image distance, and then all of those things we done earlier, but for only one object location. Okay, because there's not anything special even you change the object position. All right, so in this simulator, there's a lot of different icons right here. You can see the 1, 2, 3 menu bars, and then you can see on here, it says grid. So click on the grid, then you can see the square show up. So that is actually our, like the graphic graph sheet then, right? It's easy to measure. Change the zoom into 200, then the square is a little bit visible. You can consider each square is about some number, but actually here we have a ruler. We can use the ruler directly, okay, to measure. Click on the ruler, and then let's draw a horizontal ruler. So that horizontal ruler can actually act as a principal axis. Okay, if you click the arrows on your keyboard, up and down arrows, you can move the ruler anywhere you want very slowly, or you can click your mouse on the ruler anywhere. You can move the whole ruler anywhere as you wish. Okay, and then we need the mirror, right? To create the mirror, so you have to click on the mirrors right here, and then click on the segment. So the segment mean the plane mirror is small piece, right? Click on the segment. Then you have to draw that. To draw that, what you have to do, click on anywhere on this grid. I'm going to click exactly where it is easy for me to measure. Let's draw, let's start right here. Just one click, then keep clicking from your left hand finger on the keyboard, on the touchpad, and then drag from the right hand finger. You can see the new line is drawing. Okay, don't take off the left hand finger, because if you take off, that's going to be stick there. Click and drag all the way to the other side, 4 squares downward, and then get rid of the left hand finger. Now you have a mirror segment. Okay, now the why I draw that way, because I have a principal axis. Now you can see half the mirror up, half the mirror down. That very easy for me to uh, observe the ray diagrams very easily. Okay, and this principal axis, this line you can change anywhere you want, right? Let's change this into, if you want, like for 300 for example, then 300 line going to be on the mirror, and then 300 and 200 in between that 250 location. If you want to, you can click and drag like that. It doesn't matter, but one proper line of that meter ruler should be aligned with the mirror segment. That this is our plane mirror now, vertical white line. Okay, now in terms of measuring this meter ruler, actually you see the numbers, right? 100, 200, 300, those numbers are in pixel, technically not much meaningful. Okay, therefore what we're going to do, we're going to consider each of this is small line right here about like 10 millimeters. Okay, that's what we're going to do? We'll assume this is small line right here, about 10 millimeters or maybe 1 centimeter, right? So which means this is about 10 centimeters, not 100 centimeters, because if I consider 100 centimeters, that's going to be about 1 meters. This length scale is too big. So if I consider this 100 point right here, about 10 centimeters, 10, 20, that's about reasonable numbers comparable to our real physical experiment we can do in this kind of situation, okay? So don't click anywhere. You can see if you click anywhere now, because I already click on the mirrors there, then the new mirror show up. Then you can delete that easily. All you have to do, either you can undo, then it will get rid of. Or if you delete, if you want to delete anything, you can click in the middle right here or click the delete button on the keyboard. Then anything delete, anything if you want to delete. Let's say I draw this one, I can undo, or I can click on the middle of this line anywhere and then hit the delete button on your keyboard. That will delete. Same thing you can do for anything. For example, if I want to delete this meter ruler, I click there and then hit the delete button. Let's redo this, undo this one, then that will show up again. Okay, now I have the mirror and the principal axis. All you have to do now, bring the object, right? Let's draw an object. So let's consider to draw the object. There's no other way to particularly draw the object here in this simulator. Therefore, what we're going to do, let's draw the object by using a ruler. So let's draw a small ruler right here, about the size of maybe 2 or 3 squares. So let me follow exactly what the procedure is suggesting. That will be easy for you to follow then, okay? Okay, let's draw about like 2 squares, okay? Right? Doesn't matter the place because we're going to do this test one time here. Now this is our object actually, okay? Now that's the object. I'm going to consider this is the object. Now I have to draw the ray diagram to identify the image other side. So to do that, what we need is the rays, right? So to create the rays, you have to click on the second menu bar line. You see the ray on the very left-hand side top. Click on that. Then if you click anywhere, you see that. So that's the starting point of the ray, that red dot, right? Then the second red dot, you can bring anywhere you would like to pass through that. For example, if I want this ray to pass through exactly top of this object, I can realign this way. Then you can see it actually hitting exactly this point right here. And then it reflected this direction, right? That is my first ray. So technically we need about like 2 rays to identify the image location, at least 2 rays, right? If there's a 2 rays and then when the 2 rays are intersect on the other side of the mirror, then I can identify at least one position of the object. That's what we're trying to do. We'll try to identify this position of the object, okay? Let's draw this exactly the way it's suggesting right here. So now this is our object, this is our image. You can see 2 rays I have to get from here, and then I have to extrapolate those rays to figure out what's the top position of the object is, right? If you want to get rid of this point or change it, see, you can click and drag this point right here, bring the cursor on top of the red dot and then click and drag. Then accordingly we can change where it is originating, where I want to send that, and then so on, okay? Let's place it right there and then let's change it exactly passing through very top of the object, like the very top of the object right here, okay? And then let's draw another ray. Let's draw another ray starting from here. You have to click on the ray and then one click anywhere, then it will start the ray. And the other ray, the exactly that ray should passing through top of the very top of the object, right? So you can bring the second dot all the way to the mirror position if you want, it doesn't matter. or you can place it anywhere whenever it's ready to pass through very top of the object, like that. Now all I need is actually, now you can see it reflected two rays are these, right? These two rays not going to intersect anywhere on this side. So which mean it confirmed that it must meet the other side. So let's extrapolate. To extrapolate the rays, what you have to do, click on the extended rays. As soon as you click the extended rays, now you can see the extrapolation of these two reflected rays, you can see meeting exactly right there. So that position should be the image top location right here, right? So that's the idea. So which means to identify that exactly, let's bring a meter ruler again and then draw it here. From this position exactly to the principal axis. Now you can see this is our image. Whenever these orange rays are meeting in this simulator, those are extrapolated rays. So we have the image location, and then this side, the yellow rays are the real optical rays. This is the object. Now I can do the measurement. I have the object here, object location. I place it exactly right here. I need the separation between the mirror and the object. So each of these small line is about like, we're going to measure it to like about 10 millimeters, which mean about like 1 centimeter. Okay. If I measure them into 1 centimeter, you just need to count how many small lines. This numbers again has no any meaning. Okay. We don't care that number. Consider that numbers doesn't exist. So how many small lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is about like 12 centimeter location. So let's count to the other side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Exactly, it should be, we know that should be about 12 onto the other side. That's all really. It's extremely simple idea. Now we need the unit in meters. So let's do this one in 12 centimeters, which means 0.012 in meters. And then DI unit should be again in meters. And I'm measuring now into the virtual side. That should be negative 0.12. And then HI again in meters. Now how many small segments there are on my meter ruler? 1, 2, 3, 4. 4 segments. So that should be about 0.04 in meters. And then image height again 1, 2, 3, 4. 4 segments, 0.04 in meters, unit meters. And then percentage error between the D0 and DI. There's no percentage error because it's perfect. We're measuring from the simulator. And the percentage error, if you compare image height to the object height, that also give you the 0, right? So you can put here just zeros. There's no unit, right? So you can put the percentage sign for the percentage error, but technically there's no any meaning doing that calculation. So we can put directly 0. Okay, so now all we need is one more information from there. So we need the picture of this ray diagram. Now this is the ray diagram, right? So you created it, you take the screenshot, and all of this screenshot has to add it properly. Okay. So now this screenshot, whenever you do ray diagram with this simulator, this black graph sheet simulator right here, these are actually not going to the procedure section. These are real data. Okay. So which means table number 2, and then later you see another 2 table at the end. Though all of those are ray diagrams which must be directly go into this data section. Okay. All right. So let's put that picture right here. Let's insert that. Insert picture. And anything unnecessary get rid of, crop that out, and then we just need, this is our ray diagram. Okay, you can crop that out very nicely to show only the ray diagram what we needed to see. So that's the ray diagram we like to see. Okay, later in last two tables also similar. Okay, and the other picture you need actually right here. That should be the simulator picture. That should go into the procedure section. Okay, so that simulator we directly extract the data. So that one should go into procedure section. This one. Drop that out. But also we can get rid of anything unnecessary. We can leave it like that. Okay, now this one is actually must go into the procedure section. This is going to be now, you can name it as a figure one. Figure one, this is the simulator for the plane mirror. Okay, so we done the plane mirror section. Then let's start the curved mirrors, spherical mirrors. That's the second part. That also again the same. First we're going to study by using direct observation from the simulator similar to the we used earlier. And direct measurement, we're going to get the object position, image position, and then by using that we're going to investigate the mirror equation. So that's the plan. When it comes to the spherical mirrors, there's two type of spherical mirrors, right? One is called concave, one is called the convex. Or the concave type mirrors is actually converge the optical rays after the reflection. Convex type mirrors is actually diverges optical rays after the reflection. Accordingly, you will see the image formation is very much different compared to the plane mirror. That's what we try to investigate by using next two diagrams, okay? Next two tables. So let's get, you can keep this one. This is the same simulator we're going to use later at the very end. You can keep this one, but you can go into the next section, section C, and then click on this simulator. So that's the simulator we are using. We are using for the spherical mirrors, right? Whenever you click that, you can see already, because this simulator doesn't allow anything was to draw there. That's already preset. You can see already the curved mirrors is there. Now you can see the curvature. This curved side is actually towards the object, right? This is the object. So now because of that, this mirror act like a concave mirror, okay? And object is usually real at this point. You have the real optical rays starting from the object. Again, to identify the image, I need at least two rays coming from the object. Whenever those two rays are intersect, that will give us a one single point to identify the object. Usually, how we do this one, a couple of things. So this main horizontal line with these numbers, again, the principal axis, right? Principal axis is passing through the vertex point of the mirror. So that's the center point of the mirror. It divides by to two segments up and down. And this mirror is part of the sphere, right? So the larger, if you draw a larger sphere with a radius r, this is actually part of that larger sphere. So which means the mirror always has what we call the center of curvature point. Center of curvature point is actually r distance away from this vertex point, and then half of the center of curvature or the radius is actually called the focal point, right? So the identify the focal point, we'll take a look in next when we go into the real ray diagram producing simulator, which we done earlier. So similar that we'll draw a ray diagram to see how the focal point is formed and they identify by using rays. But in this case, it automatically gives to you. Okay, I can change the focal point if I want to by changing the mirror, but in this one it automatically gives us as a number 4 here. Again, these numbers has no any meaning. Negative positive sign has no any meaning. Negative sign will give only if we measure anything from the mirror to any extrapolated ray, dotted ray, okay? Then only that number is negative. And in this case, like previously, let's assume each of these numbers is just 1 centimeter again. Each square is just 1 centimeter. So which means this is 2, this is 4 centimeter. So this mirror has a 4 centimeter focus point. Now, unlike the plane mirror, so with the object location, you can check this. You click this object right here. You can click on the very top. See that? When you bring the cursor into the very top of this arrow, there's a dot. Then the cursor change into like the hand shape. Then click and drag. See that? Depending on where the object location is, you can see mirror image is very different. So that's the one we try to understand, right? Let's start this one about twice, more than twice, like maybe about like 12 centimeters location. So that twice the focus point is the center of curvature point, and then we're going to start much further away from the center of curvature point, and then slowly bring towards the mirror the object location, and then let's investigate how the image is actually changed, how the image position change, how the size of the image change, and accordingly let's investigate the mirror equation. Now you know geometrically by using just geometry, right? By just using geometry, we can understand 1 over object length plus 1 over image length must be always equal to the 1 over focal point, focal length, right? So if we measure the object location and the image location, we can calculate the focal point to make sure we're getting the number 4 or not. Okay, that's the other plan. And then later, after we collect the data, we're going to investigate the same equation by using graphical method. Okay, now let's continue. Let's start from the location number 12. So we'll consider each of these square is 1 centimeter. So which means now I am on 12 centimeter. The negative sign against no meaning. If it is a real optical ray, that is always positive for our case, right? Let's measure down to at least 1 decimal place, because you can see I can estimate between these two lines, right? So let's change all of these, click and highlight the whole data set, format cells, number, and then click on number 2 there into number 1, at least 1 decimal place, okay? And also you can center these numbers out, then its formatting looks nice. When the object is at 12, we need, I mentioned earlier, 2 standard ray to identify the image, right? Usually when it comes to spherical mirrors, there are 3 standard rays we use. So the one ray always going to be the parallel ray coming from the object which parallel to the principal axis, which ray should reflect and then pass through exactly the focal point. Other ray, we can do the opposite of that one, which means the one ray can go towards the focal point. After it reflected, that should be parallel to the principal axis. Another ray, we can say, you can get one ray all the way going to the center of curvature. If it is passing through the center of curvature, that is the radius location to this mirror. So which means anything passing through the radius hit the mirror with 90-degree angle. So which means it should be reflected back itself. That's why on this line, you're not going to see anything else. It reflected back itself. So I just need 2 rays. Now these 2 rays are meeting here. That also the exactly same point where this ray passing through the center of curvature passed through also. So I have all 3 rays meeting here. Any other ray starting from the object somehow after reflect must pass through this point. Okay, that's the idea. Now this is our image. Let's read the image distance. Image is formed by the real rays. So because of that, that's going to be positive. I should use the unit meters, so which means the object location 0.12, and the image location should be about 6, that means 0.06. Okay, so I can use about like at least 1 decimal place in terms of centimeter, so which means 3 significant figures, right? So let's use the 3 significant figures because of that, all of these, right? So about 3 significant figures at least. So all right, so that's the idea. Now all we have to do is change the object location and then observe the image location. So to change the object location, all we have to do, bring the cursor on top of this arrow, the cursor change into hand sign, then click and drag. How many data points I can take? 3, 6, and 7. So let's go at a time about like 2. Okay, at a time about like 2. Now I'm on 10 centimeter object, which means 0.10. Image is now, or you have to write it down the, now it's not asking image size actually. So we should write it down the image size too, because you can see image size actually changing. So let's write it down the both, okay? Object size, image size, and then object length, image length, okay? So let's write it down the both. That's going to be better then. So let's add at least one more column here. Okay, so let's continue. We need to record the object height and the image height. Object height is about now 2 centimeters here, 2 is squares. We can consider 2 centimeters. And then the image height, now you can see image height is changing later. We may have to estimate the numbers in between, okay? So the right now, image height is about 1 centimeter, okay? 1 centimeters. And then when we record the image height, you can see right here on the simulator, it record the image height with the negative sign. The reason you can see image is actually inverted, right? So you remember the magnification by using heights, we actually define it just the image height over the object height, right? So now this is an inverted image. So the inverted image mean that should be always come with the negative sign. The negative sign tells you image is inverted. So this should be then -1. And I can do the magnification, just the ratio, which mean equal sign, uh, image height over the object height. So that's going to be about like half, right? You can see image is about the half of the object, but that negative sign represent it is inverted, right? You can see the arrow is upside down. So that's the idea. Let's now, all we have to do is bring this object slowly. We'll bring the 2 at a time at this point, okay? And now my object location is 10 centimeters, image location is about now we need to estimate, right? You can see it is in between and the real values are actually given in the simulator. So it's difficult to estimate this point right here. You can see it is not half, little bit above the half. So let's get the number directly from here. That's going to be about 6.67, 6.67. And H0 is still 2 centimeters. Hi is about like minus direction 1.3. Okay, 1.33 you can say accurately. And then all we have to do, click and drag. So let's bring into 0.8. When now you can see when the object is exactly at the center of curvature point, image is exactly the same size, inverted exactly on the same location. It is now 0.08. 0.08 di and the 2 centimeters, -2 centimeters. Magnification is about 1. You can click and drag this column F. Okay. Now let's bring the object in between focal point and the center of curvature point, about 6 centimeters, 0.06. Now you can see image is much larger, inverted, and then much further away from the center of curvature point. Right now it is about like 12 centimeter location. Object height is 2, image height is about now 4, -4 because it inverted. And then let's check the focal point location exactly. But the focal point location, you can see whenever I reach the focal point, so this reflected rays you can see now parallel to each other, which means whenever the object is at focal point, image going to be at infinity. So that exact location is no meaning recording here. So instead, let's go inside the focal point. If you go inside the focal point, the object, now you can see something else happening, right? So I'm bringing object from further away, and then at the focal point, image goes to the infinity. Now you can see when I go 1 centimeter inside the focal point, I don't see image forming anywhere on this side. Instead, these two lines not going to be intersect anywhere on this side. However, if you extrapolate the lines, extended the line with the dotted rays, then you can see the other side of the mirror, the image is actually forming. That image going to be virtual now. I can't see the image size right here because at this point image going to be too large. So I have to go much closer to actually see the image clearly. Okay. So let's read like couple of data points there. I can read maybe one data point around here. Okay, let's read somewhere here. I'm going to read about like 3 data points. You can actually even read the numbers even though you can't see the size of the image. It's too large, but all the numbers are given here. Okay, let's read one number here because I need 3 data points there. Okay. All right, so now object is about 3 centimeter location, 0.03, 0.03. Take a look why this is seems to be okay. Good, 0.03, and the image is now at about 11.86, 0.1186, 11.86, and then its zero is still the same. I have to have exactly the 2 centimeter height object. I'm not going to change the object size at all. However, the image size now much changes. Now it becomes, you can see, much larger. It's negative. Now it is upright. See, now it is upright. Because of that, now the image should be just positive 18 size. Okay, it's upright. Let's bring this much closer. 2 centimeters, 0.02. Image is now -4. Now you can see these distances are other side. Because of that, the image should be now with the negative sign. Okay, now this is -4. Okay, let's continue now. Our next point, whenever the object is at point 1 location, then the image is about like 1.33 location. Okay, all of them I divide by 100 to get it into the right units. Okay. All right, now let's take a look magnification also. Magnification whenever the object is at 2 centimeter location, very close to the mirror. Now the magnification is about 4. Now positive, okay. 2, and then now positive 4 upright. And then when the object is at 1 centimeter, very close. Now the object is always 2 centimeters. Now magnification is about 2.67 positive, okay. Or now you can see if I take the magnification, the ratio that should be show us how the size of the image is changing. Now the size of the image is actually very, very small, extremely small. You can see whenever object is further away, and then it gets larger and larger and larger, inverted. At some point, when the object is at focal point, image goes to infinity, then reappear on the other side. You can see the sign changes, right? Now it's upright and the larger image first, and then it's slowly decreasing. If you bring this object much closer, now it decreasing again, okay? Now, that's the idea of the spherical mirrors, right? The image is actually very, very sensitive, whereas the object is. Now, let's take a look very quickly the image equation. So the image equation is 1 over d0 plus 1 over di should be equal to focal length. Let's take a look by using this one. So the 1 over d0 should be 1 over meters, and 1 over di should be 1 over meters. And in the focal point, if I calculate, should come out as meters. I can use formula to calculate that, and also I can check that by using the graph, okay? And let's do 1 over d0 equal sign 1 over d0. We already measured here, b33, and if you click and drag, then you automatically get the rest of the calculation. Similarly, equal sign 1 over di means C33, and then if you click and drag, then you can do automatically rest of the calculation. And I can do the focal point equal sign parentheses 1 over d0 plus 1 over di close brackets power minus 1, right? Because it's 1 over f0, but I need the f focal point. I have to take the invert. If I do that, if our equation is correct, then that should give us the focal point of this mirror. This is actually focal point is about 4 right here, right? According to our unit, that should be about 4 centimeters. That's what we get it. Let's click and drag, then we can do the calculation with the other numbers. We have exactly same numbers again here, okay? Let's check this one, another method, that is actually by making the graph. If I make a graph between 1 over d0 versus 1 over di, intercept of the graph should be the 1 over focal point. By inverting the intercept of the graph, I can find again the focal point, okay? Let's check that. Insert graph, always the scatter plot, and then double click right hand side corner, select data and x values. In this case, x value should be 1 over d0 because that's the one I am changing. And then accordingly, the image location changes. 1 over di should be the y values. So click OK, click OK again. You will see a nice straight, the continuous linear continuous lines. So dotted, I need actually the trend line, right? Double click, chart elements. I need axis title also, horizontal and vertical, and then also I need the trend line, linear. Now all I need is actually the slope of the graph, the intercept of the graph. To check that, you double click on this line and then go into the right hand side, keep the linear, and then click last two, only last two, because y-intercept is not 0 any longer, right? That's the number we expecting. So if I get the inversion of the y-intercept, that should be equal to the focal point. Let's take a look at that in a bit. Let's give a title here. This is gonna be 1 over object length, so 1 over d0 versus 1 over di for concave mirror. Okay, and then the x-axis should be now 1 over d0. 1 over d0 unit should be 1 over meters, and then similarly the y-axis title should be 1 over di, and the unit should be 1 over meters. Okay, and then the slope should be about 1, so that's what we're getting here because there's no numbers in front of 1 over di, so the slope should be about 1 over di or 1 over d0. Slope should be about 1. We're getting the right number there. And by using the graph, we can actually recalculate the focal point, right? calculated average of focal point mean average of this column. So you can see numbers doesn't change at all. But let's do the average equal. Average is a V. Average function, highlight this whole range and then 0.40. From the graph, gonna be 1 over the intercept. So which means equal sign 1 divided by intercept is 25.024. So we are very close to 4, but not exactly. So we can do the percentage error. The given value, real value is 4. So the percentage error, let's compare to that one. Equal sign ABS. Expected value is 0.04 minus calculated value. Average going to be C56 divided by 0.04 multiplied by 100. And you can see small error there because actually there's other numbers is inside here even though it's rounded. Okay, other decimal places we cut out, but the when you do a calculation on the Excel, other decimal places they are in the calculated cell. Okay, and if you click and drag, I can do the error for this number too. Okay, question. Okay, then let's continue. All right, so let's continue to the next. Next, what we're going to take a look is the same concept, same ideas and everything, but we're going to take a look the convex mirror, right? So now to investigate the convex mirror, what we need is actually the curvature should be to the other side. So you can't really change the curvature of this mirror. You can see it's impossible to change. However, what we can do, if you click this object and then drag all the way to the other side, you can see it automatically converted into the convex type. Okay, read this term right here. Okay, right here you read this term. Now it says the concave mirror, and then you click the object and then bring to the other side, then it automatically says the convex mirror. So now I have a convex mirror. All I have to do, go back again to the object length, 12 centimeters. Now I'm on the other side of the curvature. Now you can see always, doesn't matter where the object is, you can see always image gonna be virtual and then upright and then very small. The size is little bit changing, but not much like the previous. Okay. Let's do again the same now. Okay, now I'm on the convex mirror, and then all the lens we're going to measure again with meters, and then we'll check the magnification also. Okay, D0 now 0.012. Positive image gonna be now at about 3 centimeter, but now you can see that image distance to the negative side, right? Because why? Not this negative side, I mean it negative because of our sign convention. This image is formed due to extrapolated or extended rays, dotted rays. So this should come with that negative sign. Okay, negative 0.03, about 3 centimeters. H0 is 2 centimeters. Hi is about 0.5. Now you can see Hi is positive. The reason now it's an upright image. And that's all. Then let's do the same thing. Let's go to the 10 centimeter location, points 1 to 0.10. Earlier one should be 0.12. Okay, it's 12 centimeters. And the image is now at negative 2.86. And then the object size is 2, image size is now 0.57. And then let's click and drag the object another 2. Now it's about 0.088 centimeters. Image is at negative 2.67. Object size is 2. Image size is about 0.6. And let's bring it to 6.0 location. Now it's about 0.06. Image is about negative 2.4. Size of the object 2. Size of the image is 0.68. Image getting little bit larger. not really sensitive too much, but it's getting slowly size increasing. You can see it started at 0.5. It started at 0.5 and then slowly the size increasing of the image. Okay, as the object come closer. Let's go to 4. So that is about the focal point earlier we calculated, right? So the point for the 4 centimeters, 0.04. Now I have minus all these numbers I need to change, right? So I have a mistake there. These should be, all of them should be in meters, which means I have to bring the negative sign. All of these should be 0.02, okay? 029, 0.027, 0.0, go back to the previous one to just quick check, 6.024, okay? 024, now new location about like negative 2.01, so which means 0.0201 negative, okay? And the object size is still 2. Now the image size is 0.84. You can see image size is increasing slowly. Let's go to 2 more numbers we need. 0.02 object length, image length minus 0.0133, and the object size is 2. Image size is now about 1. Okay, and one more data point. Object now at 1.0 location. If you can't get it to exactly 1.0 location, just get as close as possible. 1.08, or you have to write it down exactly the number you see here, okay? That's going to be 0.01. The image going to be at negative 0.008 because now it is 0.8 here. It's going to be like less than 1 centimeters. It's going to be like 0.008. Okay, 0.008 negative 0.008. Okay, and then size of the object 2, size of the image is 1.36. Now you can click and drag it a little bit further and further closer. You can see image getting a little bit larger, but always going to be image going to be in between focal point and the mirror. You can see it not going to be going anywhere else. Okay, that's the idea of the convex mirrors. Let's check the magnification, equal sign hi over h0, and then we expecting that to be about the same number, that to be about the changing number, that to be actually increasing, because the magnification you saw slowly increasing. That's what exactly you see. Magnification is about 1/4 and then slowly it increasing all the way to half and then little bit above the half. Okay, now let's do the same check we done earlier. So the doesn't matter what type of mirror is, still the mirror formula should be validated, right? So let's check that. So let's do 1 over d0. Similarly we done earlier, 1 over meters, 1 over di. Similarly we done earlier, 1 over meters. Then let's calculate the focal point. K equal sign 1 divided by column number B66, B66, and then click and drag. And then similarly di equals sign 1 over column number C66, then click and drag. Okay, C66 and then click and drag. Let's calculate the focal point. Equal sign 1 over d0 plus 1 over di parentheses power minus 1. Okay, let's calculate the focal point. Now, if I calculate the focal point, that should be equal sign parentheses 1 over d0 plus 1 over di, close brackets, power minus 1. We're getting exactly the same number earlier, but you can see now focal point is actually negative, which means focal length is negative, which means focal point is always going to be other side of the mirror. You can see this is the focal point now, right? All the incident rays right now, all the rays coming from the object is actually diverging, and if you extrapolate that, those rays going to go to the focal point. Now it's a completely opposite case for the previous. Okay, so that's why we have these two basic type of mirrors, right? Either converging or either diverging. Let's do the same analysis we done earlier. Let's make a graph and then let's check the same number from the graph. Okay. Since we already done the graph earlier, you can make the graph from the scratch, but you can actually bring this graph to the next. Okay. Now this is going to be our figure number 2, because earlier we had one figure here, simulate a picture. We can say this is figure number 2. Figure 2, this is going to be now graph of 1 over d0 versus 1 over di for concave mirror. Okay, let's do this. Let's copy. Let's make a copy of this graph and then edit. That is much easier. Copy and then paste that graph into here. And it's the same graph. Now all I have to do, edit the data, right? Double click and then select data. Click on the series, edit, and then delete everything on the X, delete everything on the Y. And then let's add the new data. That's all we have to do. Okay, if I add the new data, then I have the new information what we wanted. Okay, that's the plan. So X values now, Y values now should be 1 over DI. C number 76 to 83, and then the X value should be B number 76 through 83. Click OK. Click OK again. That's the new. It's the same kind of graph, but it's for the new mirror. Okay. And you can see the numbers again. It's almost the same. Number in front of the X should be about 1. And then if I take the inversion of the intercept, that should be about the focal point. Now I have to just edit this name right here because this is now convex mirror. That's the only difference. And also I can bring the figure name which I made here into here. So that figure name now going to be figure 3. Only difference is now this is for the convex mirror. Okay. Let's do the same analysis we done earlier. Focal length. We know now calculated average equal sign AB. We already calculated earlier table. We just need to get the average of that column number D on table 5. About the same. Percentage error equal ABS. Expected -4 minus calculated average C88 close brackets divide by expected ABS parentheses -4. Give it in positive, okay? Otherwise, our percentage error can becomes negative. That not make any sense, okay? Let me take a look. This should be actually 0.04. This also should be 0.04. Okay. Okay, it should be very small number. You see that it's small error because actually some of these numbers may have more than some other decimal places with the numbers. it's better actually show those because this is a calculated value. You may actually increase the number of decimal places to maybe like 4 to see whether other numbers are visible. See that 1 or 2 has extra numbers, right? That's why we actually observing little bit of percentage error there. That's totally fine. Let increase 1 or 2 decimal places. See that? That's why you actually get in this percentage error, okay? And from the graph going to be equal sign 1 over, the number is negative 24,947, negative 24.947, close brackets. This number is negative. I have to bring that negative sign too. Okay, you can see it's very close. Let's do the percentage error. Still like about 0.2. So that's all about the concave and convex. Since I already have one figure here earlier for the simulator, this is actually for the simulator for the plane mirror. Now I have to have another 2 pictures actually, because you can see there are 2 pictures I should get, because when the object is here, this act like a concave mirror. Let's take a one screenshot and bring this into the other side. Let's take another screenshot that will be convex. Okay, all those pictures you can collect here, actually the same location, because all of those pictures should go to the procedure section. Okay, only the pictures we need actually here in the tables are actually the these pictures we will be drawing by using the other simulator in a bit. Okay. All right, so let's add those pictures here. I earlier had one here. Let's put that next one somewhere here. Insert pictures. And this is for our concave mirror. Concave mirror. You can show that concave term also, because then it confirm what kind of mirror, and then all the information just let it show. That is actually better. And then this is gonna be then figure 2. This should go to your procedure section. Okay, it's gonna be figure 2. This is actually for the concave mirror simulator for concave mirror. And I need one more picture here. Let's add that one also. Insert pictures and screenshot. Last one. Rid of anything unnecessary, but let's show other information because those information are useful for this one. Now this is for our picture for convex. You can bring this term there from here to here. It's going to be figure 3. These 3 figures should go into your procedure section. Okay, now this is for convex. And then because of that, the figure numbers on this graph should be start at figure number 4. Actually, this should be figure 4. Then this should be actually figure 5. Okay, now only thing what we have to do is actually going to next section. What we're going to do, we're going to actually, these ray diagrams you already have seen, right? It's simple ray diagram here. However, it automatically drawing for you. So what we're going to do, we're going to make the ray diagram ourselves. So by using at least 2 optical rays, we can identify where the image is, like we done for the plane mirror earlier. We done here for the plane mirror. Exactly same thing. Let's do this way and then take a look how the image formation changes with the object location for the concave and the convex mirrors. Okay. So that's the plan. Now to do that, you need the other simulator, that is this one. You can leave it as it is earlier if you have it, or you can start from the scratch. If you want to start from the scratch, you can reset There's a reset button on the top. If you click that, it will reset out, then you start from the scratch. Okay. Now what we're going to do, we are on now table number 5, right? So on the table number 5, what it's asking is actually create those ray diagram yourself. Okay, ray diagram for concave mirror. So first you have to identify the focal length by creating the ray diagram. Then you have to put the object little bit above R, in between R and focal point, and then below the focal point, and then identify the ray diagram. By now you know what kind of ray diagram we are expecting. So let's take a look. Okay, so let's make the ray diagram for these two type of mirrors. First, we'll take a look the concave. Okay, so if there's anything, you can actually reset or you can delete everything. And the step number 1, make the grid and then make the zoom into about like 200, and then make the ruler. You can see on the second line ruler, and then click the horizontal ruler first. Okay, so which mean by click somewhere here, I'm gonna make the whole full line of to cover the whole area. So that is my principal axis, right? And then let's make a mirror. Now when earlier we make actually plane mirror, right? So that's inside the mirror. Earlier we use segment because we need the linear, but now I need the circular arc, right? Because this is a spherical mirror. Click on the circular arc. And to create the spherical mirror, this is what you have to do. Now click on some location right here. Let's say this location about like 1, 2, 3, 4 squares up. Just one click, okay? If you click once, then you will see that red dot, okay? Don't click anywhere. Without clicking, you bring the cursor 4 segments, 4 squares downward from the principal axis, because I need exactly the center of the mirror at the principal axis, okay? Then you see another red dot, right? Click there. Then you will see a mirror appear. You see that? Now the mirror shape you can change, right? I need the concave, so which means if I'm planning to put the object on my left hand side, this should be curved towards there, right? So it should be look like that, and you can adjust actually how much the curvature is. So that decide the radius of curvature, things like that. Let's give a little bit of curvature, not much, and then let's click somewhere right here. This pink dot right here, exactly click that pink dot on top of the principal axis. Then our vertex point is that pink dot. That's going to be exactly top of the principal axis. Now we have the mirror. Now what we need to identify is actually the focal point, right? To first part, to identify the focal point, what we need is actually just parallel rays. All the parallel rays to the principal axis after reflection should pass through the one point that called the focal point, right? So let's create the parallel rays. Click on the ray and then click anywhere on the grid. I'm going to click somewhere on this third point right here, and you can see a ray, right? When the one dot is actually remaining there like earlier, and the other dot I can decide where it actually should go. Now I need this to be parallel exactly to the principal axis, so I'm gonna adjust until it parallel to the principal axis, then click the second dot, then it will becomes permanent. You can still move anywhere this ray as you needed, okay, as it needed. You can click back here and then change it if it is needed. Okay, and then all we need is at least one more ray. So click, maybe I'm going to click that on the bottom here, other side of my principal ray, and one click, create the ray, and then you adjust this other dot, and you can see now when I adjusting this, if it is exactly parallel, that point gonna be look little bit away from the principal axis, right? So that actually because maybe our principal axis not exactly where it's supposed to be. So I can readjust that little bit. Principal axis it may have to move down a little bit, right? You can see it even here. If you want to move that, all you have to do, click on anywhere on the principal axis right here, and then use the arrows on your keyboard, right hand side, up and down arrows, you can move actually principal axis. It may not be exactly on the middle of this pink dot right here. It should be exactly passed through mid of the pink dot. Since it is still a little bit larger, I have to adjust a little bit. Now you can see I have one ray come from the top, which reflected from the mirror, passed through this point. Another ray come from the bottom, after reflected, passed through the same point. All these rays parallel to this horizontal line, that is the principal axis. Now, that's the way, if you're doing this in class, we can easily identify uh, focal point of any given mirror by using this simple technique. We just need the couple of laser beams, that's it. And let's measure this one. Now, if I measure this one, you know, I have to measure by using this meter ruler. I'm gonna bring one of the line exactly at the mirror location. So then I need to count how many number of segment, right? So these numbers has no meaning again. How many number of segments? In this case, you can see it's better if you start at this. I can undo that. Okay. So click on exactly here, and then maybe let's start from there. Then it is easy to count, right? Because that number is 5 numbers in between that line and this line right here, large line, right? 5 segments, then another 5 segment, 10, 11 segment, and this is in between 11 and 12. I can read into 11, 5. So each one line is about 10 millimeters, 1 centimeters. This is about 11.5 centimeter in terms of units. Okay, so we are not interested that, actually we just interested this ray diagram, how you identify that. We are not going to measure anything, so all you have to do, uh, take a screenshot and then add that screenshot into here. So ray diagram for the focal point. So the insert, illustration, pictures, and then let's add the last one. We have it here, but you have to nicely readjust, crop this, because we interested only this ray diagram, nothing else here. We're not going to do any measurements or anything. Because of that, I would suggest you to just crop out anything unnecessary. That's the only part we're interested. And let's put that on exactly in this space. That is our ray diagram to identify the focal point. And we done one, then 3 more to go for this. Then the next one, it asking ray diagram when the object distance be 0 greater than r. Now you know focal point is this one. You have to remember that for this one, right? This is about like 11.5. Now what we're going to do, we're going to place object much further away. If this is 11, I have to put the object about 22 or more distance, right? Somewhere here. Let's do that. So to create the object again, I can bring the meter ruler and then I can draw object right here. Then that object can act as object much further away from the mirror. Okay, so that our object be too far. Let's bring into a little bit of closer. I can go about, this is 11, then there's another 11, 3, 10, 13 already. So I can bring even a little bit closer right here. It should be a little bit further away from the center of curvature location. Center of curvature location is twice the focal point, right? All right, now I need 2 rays, right? I can use the same 2 rays here. So I need one ray which is passing on top of this object, and then which let it go parallel to the principal axis, right? That ray after reflected gonna pass through the focal point. Then I need one more ray, okay? So to get the other ray, I can use this one, this previous one. You can click and drag. Let it start somewhere here. And then let's change this point right here. See, if you click and drag that I can change. Let's bring that and then readjust the ray to pass through the focal point. And it should come from top of the object and then it should pass through the focal point. If that happen after reflection, that should be parallel to the principal axis, right? See that second ray passing through, come top of the object, passing through the focal point after reflection, parallel to the principal axis. Whenever the two rays are meet, then I have object here. Now this is the object location. Let's mark the object also. I have image, sorry. Let's mark the image also. Now that's our image. This is the image, this is the object. Now let's you can take a look this actually in the discussion. You can discuss whether you get the right way or not. Now my object is much further away from the center of curvature point. Image should be smaller than that inverted that what exactly we observing. So we have the right way. Now only thing what we doing here, we create in the ray diagram ourselves. Let's take the screenshot. Let's add that into here. Space. So insert. So the next picture. And that should go into this space. Let's crop that out. Unnecessary. Anything unnecessary. Okay. That's the only part we needed. Good. Crop out. And then bring and place into this space. If it is larger, make it smaller, only to put it into this side. Okay, then you can copy paste everything into your Word file. I have to check two more locations for this one. Whenever the object distance should be between R and F. Remember, F is this point right here, right? Let's bring this object, click on the object about maybe 5 segment from the focal point, and then readjust these two. This first parallel ray, you can leave it like that because that's going to be reflected back through the focal point. Let's keep that one. Now let's change the second ray. Now the second ray, you can actually let it pass through the top of that and then has to pass through focal point. If that happens, then your image should be, remember, much larger and then much further away. And still inverted, right? See, now this is the image. Inverted, much further away. Now it much larger. And you can extend that. Now this is the image. You can see image is now actually getting much larger. Now take the screenshot, print the screen. Let's add that also into here. Insert. Pictures. Last one right here. Now crop that out, unnecessary stuff, and leave it here. Okay, you have to show where the image, that's important. Okay, then crop that out. That should go here, and then make it small a little bit to nicely fit with this space. Okay, last image. I have to bring the object now in between focal point and the mirror, right? So let's place it somewhere there. Now, none of these previous rays can be used for this one. It's none of those are actually match. The reason you can see, if I have a parallel ray, which parallel to the principal axis, after reflection, it actually blocked by the object itself. So I can't use it as it is, right? So that will be a problem now. So I have to figure out a different rates to make this diagram, right? So let's draw this way. Let's make a ray going from the going through the top of the object, and then it's gonna go all the way to the vertex point of the of the mirror. So that kind of ray, such a ray which actually pass through the object and then go to the vertex point, should be reflected back. When it is reflecting, it's going to be the same angle because law of reflection applies. Now I need one more ray. Now to do that ray, I can't do actually this way. You can see now it is impossible to make another ray passing through the focal point or anything, right? But I can make another ray which may be passing through the center of curvature location. Let's do that ray. Now I need to identify the center of curvature location. Center of curvature location is earlier focal point was 11.5, 5, 10, 11.5, which means the center of curvature point should be about at 22 of this segment, right? So the 5, 10, 15, 20, 22, this line right here. So all we need to get is that one ray passing through that point, exactly center of curvature point, and that ray should go through top of the object. If that is the ray passing through exactly center of curvature location, that ray must be reflected back itself. That's what we're trying to draw here, okay? So that should go through exactly 22 segments from the mirror, 5, 10, 15, 20, 22, this point right here, that point right there, and it should pass through exactly top of the object. If that passing through exactly top of the object, and if this is exactly the center of curvature point, then that ray should be reflected back itself. You can see I can identify center of curvature point just changing this mirror, this ray, right? So if I change the ray until the reflected ray goes top of each other, that should be the center of curvature point. Question. Everybody okay with that? 5, 10, 15, 20. This is about now actually 24, not 22. Earlier what we got 11, 11.5, 11.5 is about 23. Yeah, so it's slightly above like 23. If I take the 23, let's try with that. That's the 23. Yeah, I can get it, but it's gonna be a little bit off from the object top point. That's the object top point, okay? So this is exactly the matching point. So we'll go with that actually. Okay. Now the only problem is that you can see now the image, I can't identify anywhere this side, right? I have two rays. Now you can see two standard rays now different than the previous, okay, any of the previous. Now only problem is that I can't see anywhere here these two rays are meeting each other. So which mean image going to be other side, which mean I have to see the extended rays, right? You can go into the right hand side, left hand side very top, click on the extended rays. As soon as you click on the extended rays, you can see extended rays are crossing here. Now that is our image. Now you can see image is actually upright, larger image. That is exactly what we have seen earlier. That's what you have to do in the discussion. You have to confirm whether earlier version, the everything you have seen, whether that makes sense, everything is matched when you really draw the ray diagram, and then so on. That's what we're doing here, okay? So all these orange color lines now, extended rays, all the yellow color lines now the real rays. Now we are using two different actually four different specific rays. Earlier we used one parallel ray, one ray passing through the focal point. Okay, that's the two standard ray we used earlier when the object location is further away from the focal point. When the object is much closer to the focal point, those two rays cannot be used. So I'm using now one ray passing through the object top point to the vertex point, and the one ray passing through the center of curvature location through the top of the object this should be reflected back itself. Extrapolated backward, identify the image. So the print is screen, that is the other image we needed here. Let's bring that, insert, illustration, and then let's add that picture. Okay, and then crop that out, anything unnecessary, and then you have to show object location, all the extended rays, and then all of those information are important. Okay, and then make it a little bit smaller to match with this area. All right, so we have all the images ray diagram we needed for the concave, and then all we have to do the same thing for the convex. Okay, then we're done. All right, so let's continue. Now I need to do the same thing for the convex. So let's get rid of all of these. You can click on any of these and then hit delete button. That will delete all of these rays. You can see all these object, image, and everything. None of them we need now. Now all I have to do is actually you can keep the same mirror, and all you have to do, click on this midpoint and then click to the other side. If the curvature is to the other side, then we know if the curvature is to the other side, if the curvature is opposite to the object, let's put the object on the left hand side as usual, then this will act like a convex, this will act like a diverging mirror. Okay, that's the plan. So all we have to do is the same thing again. To identify the focal point, let's bring the ray, and then let's do the same thing, parallel ray starting from there. Next dot, you can bring it to closer to here and then click there. After it reflected, you can see now extended ray. I already clicked that extend. Now this is diverging, right? You can see after reflection, it goes away from the object. And if you extrapolate it backward, the orange color line crossing the principal axis, but other side of the mirror. So that's why now this is actually a virtual. This focal point is the virtual focal point now. Okay. Let's make another ray right here. And then after reflection, that also should pass through exactly the same point. If it is not exactly passing through there, reason most probably is this dot may not be exactly on top of that line, or our principal axis may not be exactly on there, or one other thing may be these 2 points may not be exactly symmetric. So maybe I need to change that point very little bit. Let's take a look. This may be top point. I have to change very little bit. That may not be very symmetric. Make sure these two are parallel. You can adjust this one, this top point and the bottom point until that crossing point come to the exactly to the principal axis. Now we have both rays are crossing exactly on the principal axis. That exactly the focal point. Okay. So let's bring this little bit to closer. Then I take in the screenshot. That may be much easier because I would like to have all of them are visible. Okay. Now this focal point is actually virtual. The reason that is created by extrapolated rays. Earlier it was dotted rays. Now this orange color line representing the dotted rays. Okay. That's all really. Then let's put that picture into here. Insert, illustration, the pictures. And let's bring that and then place into there. Get rid of anything unnecessary. Crop that out. Okay, now that's our ray diagram to identify the focal point of the convex mirror. Let's do the same thing we done earlier. 3 more ray diagrams. Okay. So now now in this case, even though we try to change the object location, it might not change anything much, but let's do that to make sure that going to behave same way as earlier observation. Okay. Now what I need is the object, right? Let's bring the object. Now let's measure this focal point first. How many segments? 1, 2, 3, 6, 8, 10, about 10.5. Okay, focal point is about 10.5. So let's bring the object. Object is actually a meter ruler. Let's put that about like more than 20 segments away. So then that will act like an object which is actually much further away, further than the center of curvature of this mirror. Even though on this side there's no meaning we talking about center of curvature or focal point at all. The reason now you can see center of curvature and the focal point going to be other side of the mirror. Okay? Now let's do the same thing. Let's make a parallel line, parallel ray coming exactly on top of the object that gonna be look like diverging coming through the focal point. Let's make another ray. Now I can do this ray two different ways. Okay, one way is that I can make this ray look like going towards the focal point. If that is the case, after reflection, it's gonna be parallel. Okay, if it is going towards the focal point after reflection, that's going to be parallel. That's one way of doing it. Other way is that I can make that ray directly towards the vertex point, exactly this midpoint. Okay, that should become exactly on top of the object again. Now that ray after reflection, it's going to be reflected with the same angle by keeping the law of reflection correct. If I extrapolate that line, that's going to be meeting right here. Both of these lines now virtual rays, right? Because of that, now you can see image is virtual and upright and really small. That's what exactly we have seen earlier. Take the screenshot, put it into here. Now your object is much further away from the possible distance of the radius of curvature. Okay. All right. Now let's insert that. Crop out anything unnecessary, and then make sure it is visible, the object and the image location and everything okay on your picture. And that's it. That goes to around here. You have to make it much smaller, otherwise it not fit properly. Okay, two more diagrams, ray diagrams. Then let's bring this object R and F, that mean focal point for this one is about 10.5, anything greater than 10.5, but in between 10 and 20, okay, somewhere maybe around here. Let's draw the ray diagram again. You can keep the parallel one, but you can change the other ray, okay. So let's change the other one, which passing through the object top, and then which is actually hitting exactly the vertex point of the mirror. And then after reflection, you can see both are diverging, and then the extrapolated rate meeting here. Now, size of that image is actually, you can see slightly greater than the previous one. Very slightly, okay? Very slightly greater than the previous image, but upright, virtual. Take a screenshot that goes to this space. Search. Crop out anything unnecessary. Crop out anything unnecessary, and then that's our new diagram. Okay, that's our new ray diagram. And these are data, okay? You have to put all of these in this table. This table go into your data section, okay? These are not just simulator pictures, okay? All right, then let's bring the object very much closer and then check again. Technically, this distance, object distance now no longer matters, right? You can see image always upright. Size is very slightly changing, but nothing much. You can keep the parallel ray as it is, and then you can take the other ray coming through the top of the object and then hitting exactly on the vortex point. Now you can see image is little bit larger now in size. You have to click this somewhere and then change the location of that. Now that's the image location, and you can see image size is little bit larger than the previous. Okay. Take another screenshot that goes to here. Third pictures, and then that's the last image you need, last ray diagram you need for this lab. Okay, crop out anything unnecessary. Okay, that's the ray diagram we needed. We can make it small a little bit. All right. So we have 4 ray diagram for the convex, 4 ray diagram for the concave, and then you should have 2 graphs for concave and convex, and also you should have 2 other diagrams, the simulator pictures, actually 3 other simulator pictures. So all of those simulator pictures should go into procedure section. Okay.